In the last video, we talked about z-scores. In this video, I wanted to mention, well, if you're given a z-score, how do you go back and figure out what the original scores would be? So let's say we're looking at the Iowa vocabulary scores, what we did in a prior example over here, where we had the mean scores for Iowa students was 6.84 with a standard deviation of 1.55. Let's say we had 3 students and we took their scores and we converted them to z-scores, and we ended up with 2.1, 0.5, and negative 1.6. We wanted to know, well, what was the original score? And just to revisit this example, in the Iowa vocabulary score, the typical student scored somewhere between 2 and 12 on that test. And it followed roughly a normal distribution. So let's go ahead and write that down. Mu was 6.84 and the standard deviation was 1.55. And if we have z-scores, that's really all we need. And also what you can remember about this formula is basically what we're trying to figure out is what is x? What is the original scores? Because these things right here are z's in this formula. And you can actually do a little bit of quick math to solve this formula for x. But if you multiply across by sigma, we'd get z sigma is equal to x minus mu. And then if we add mu to both sides, we'd have x is equal to z sigma plus mu. And this is the formula, if you want to just write this on your notes or whatever, it's really from the same formula, that if you have a z-score and you want to convert it to a actual score, which again, x is the observation, we can, get that value from doing this. And actually notice it's just a linear function, like a linear regression equation, where the sigma is basically the slope of the line and mu is the y-intercept. But essentially we have all the information we need in order to solve these as original scores. So basically, let's say z was equal to 2.1 and we want to know, okay, what is x? Again, we could use the formula. X is equal to z sigma plus mu. So we would have z is 2.1 times sigma, which is 1.55, plus the average, 6.84. And if we do this, this should reconvert it into a normal score, which again, we'd expect to be on the scale of 2 to 12, because this is where, this was what our distribution looked like. And again, if one standard deviation was roughly somewhere about here, 2, I'd expect it to be somewhere around 10 just by eyeballing the graph. But we can do a little bit more of an exact calculation by using the precise formula. So let's go ahead and do that. 2.1 times 1.55 plus 6.84. And what we get is an actual score of approximately 10.1. And again, the score, who knows if they were allowed to have decimals or whatever. But let's just go ahead and round to the nearest 10th for convenience. So we knew that student scored about a 10, which is pretty high, pretty far above the average, because the average score was about 6.8. That student did quite well. And again, a z-score of 1 or 2 or 3, we should be able to interpret that meaning without understanding anything about the scores, because z in general is referring to the standard normal distribution. And just to go back to the slides for a minute on the standard normal distribution, basically go ahead and defining that. Any normal distribution is a distribution which follows the pattern. Sometimes our book will refer to it as n parenthesis mu comma sigma, which is just referring to any normalized distribution which has a mean and standard deviation as sigma. Whereas a standard normal distribution, sometimes it's written as n0 comma 1, because the standard normal distribution has a mean 0 and a standard deviation 1. But basically, anytime we're converting a score to a z-score, it's converting it to this normalized distribution, where again, what is 0? Like basically the mean is going to be a 0. Like if you were to plug in a score which was exactly equal to the mean, let's say we plugged in 6.84 into this formula where 6.84 is the average, we would get 6.84 minus 6.84. That would give us a z-score of 0. So essentially, any student who scores exactly the average will have a z-score of 0. It's like 0 is the central point of the standardized normal distribution, 0. And every standard deviation is 1 z-score from there. So basically, a z distribution is exactly what I'm drawing, where it's removing the scores, removing all the context of the numbers, and normalizing it to a z distribution. So essentially, when we see 2.1, we know, well, okay, it's over here. Again, the point of that is to kind of understand on a general scale, where is that? So that when we're getting scores like 6 or 8 or 10, and we have very specific data, we can kind of know where the score is. You know, we might not know what a score of 10.1 means to the context of a problem, but when we know the z-score, that's always, we know what it means, and that's why we care about standardizing things. So let's take those other two scores and standardize or unstandardize those as well. So like looking at a z-score of 0.5, and then we'll take a z-score of negative 1.6 and figure out where those would be. And so again, before doing anything, I'd expect a z-score of 0.5 to be roughly half a standard deviation, somewhere in the vicinity of 7 or 8. And a negative 1.6, I'd expect that to be somewhere over here, something like 4 or 5. And that way I can kind of check myself before I do any math to, you know, because that's the general sense of the positioning of a z-score on a distribution. Okay, but again, the formula is the same. I'm just going to change, well, x is always equal to z sigma plus mu. So z in this example is 0.5. Again, sigma is our standard deviation of our normal distribution, and mu is the mean of our normal distribution. Go ahead and plug that into the calculator. 0.5. And this would leave us with approximately 7.6. And this again is the normal, the regular score pre-standardized. Again, that would give us, okay, what was that student's original score before standardizing? And then a negative 1.6, we'd expect this to be a lot lower. Again, go ahead and plug that in. Negative 1.6 times 1.55. And what we'd have is, again, x is equal to negative 1.6 times 1.55. Same formula for unstandardizing it. And that would give us a score of about 4.4. And again, it's useful to be able to take an original score, convert it to a z-score as we did in the previous video, but occasionally we also want to be able to go back and figure out, okay, what was the original value of this score?